Assalamualaikum and good morning. Last lesson, we looked at the chemical properties of alcohols. These are the reactions of alcohol. So we've looked at the combustion with oxygen to give carbon dioxide and water. We've also looked at the reaction of alcohols with sodium, where we said that alcohols are weak acid, so they behave like an acid in a reaction when they react with sodium metals to form a salt called the sodium alkoxide, is the general name for that salt, and hydrogen gas. We've also talked about the acidity of alcohols compared to the acidity of water. And we've also looked at the substitution reaction where your halogens replace the hydroxy, the OH group in alcohol. So there are three types or three reagents that you can use. You can use hydrogen halide, in which case you would need to produce the hydrogen halide on site, that is using a sodium halide plus concentrated sulfuric acid to form the hydrogen halide that you are interested in, whether you use HBr, HCl, or HI. The second reagent that you can use is PCl5 or PCl3. However, with PCl3, you will need to use heat, whereas PCl5, you can just add it to alcohol straight away and it reacts at room temperature. And the last type of reagent is the SOCL2, SOCl2. There's no catalyst needed for this reaction. There's no temperature needed. It works fine at room temperature. And then the products are also easy to separate because two of them are gases. You just let them evaporate and you are left with the liquid product that you are interested in. So this could be your halogenoalkane, the desired product of the reaction. Okay, so we've also looked at the setup of a fractional distillation because this setup is used to separate two or more liquids with different boiling points. So this is just the summary. So today we're, and then also we looked at the dehydration reaction of alcohol, where alcohol lose water to form an alkene. Losing water is usually OH from one carbon and hydrogen from the adjacent carbon. Okay, there are two methods as well for the dehydration of alcohol. The first method is using concentrated sulfuric acid and heat it to reflux up to 170 degrees Celsius, or you can just use heated aluminium oxide, okay, as the second method to dehydrate your alcohol to form an alkene. The next reaction that we're going to look at is esterification. Esterification is a type of condensation reaction. Okay, so you are combining two molecules, two reactants to form one product with the release or the production of water. Okay, so that's what condensation reaction is. The reagent for a the reactants for a condensation reaction would be alcohol plus carboxylic acid. The catalyst would be concentrated sulfuric acid, and then you heat it under reflux. Okay, so here you have an example of propanoic acid as your carboxylic acid and your ethanol as your alcohol. During the condensation or the esterification reaction, we are removing the hydrogen atom from the alcohol and the hydroxy OH group from the carboxylic acid. So together they are released or they are produced as water, H2O. So where we remove the atoms, that is also where the new bond is formed. So the new bond formed at a And then esterification reaction is the C single bond O. And the functional group of ester is this COO. I usually like to extend it COOC. Okay. The reason why is because if we just stop at COO, then it could be COOH, like your carboxylic acid. Okay, so take note, ester's functional group is COOC. Okay, right. In ester, the site that is attached to the C double bond O is the carboxylic acid site. Okay, or we call it the carboxylate part. And then the site with the single bond O is your alcohol site, or we call it the hydroxyl. Okay, right. In terms of naming this molecule, we always start with the alcohol site that ends with YL. So it's like an alkyl. Okay, so the alcohol site will have the name alkyl, and the carboxylic acid site, which we call the carboxylate, will have the second name. Okay, so when it comes to naming, we look at the alcohol site first. We have 2 carbon here, so it is called ethyl. Okay, so that's carbon 1. Sorry, I will not name, I will not number them. Okay, so that site has got the ethyl part of the name, and then the other site, which is the carboxylate site, don't forget to include the carbon of the C double bond O. Okay, so there are 3 carbons here, so we call it propanoate. Prop stands for 3 carbon. Okay, so naming of esters is usually the hydroxyl carboxylate. Okay, so the hydroxyl carboxylate is the alcohol part of your ester. Okay, so if you want to copy this down, you can pause the video here. Okay, the next slide is just showing you how to name the ester again. The first part of naming comes from the alcohol part, which is the ethyl, because there are 2 carbons, and then the carboxylate part also has 2 carbons, so we call it ethanoate. Okay, do not forget this carbon on the C double bond O. You have to count that carbon as well. Okay, moving on. So that's esterification. The next reaction. Oh, okay. I want to add something on the esterification. Sorry. So this is usually written as a reversible arrow. Okay, the reason is because of the position of the equilibrium. The reaction is reversible. So an equilibrium mixture can be established with all the reactants and the products. So I will not explain equilibrium on this session because you have a big topic on equilibrium which you will cover later on. Okay, so the next learning objective is to describe the oxidation of alcohols with either acidified potassium dichromate K2Cr2O7 or acidified potassium manganate KMnO4. So you can choose either one of these oxidizing agents. They are both oxidizing agents They have the same function, that is to oxidize your alcohols whenever it can be oxidized. However, the observation will be different because they have different starting color and end color will be different. And so I'll explain about that later on, okay? So this is how you prepare your oxidizing agents. You just mix your potassium dichromate with dilute sulfuric acid. Likewise, for your potassium manganate, since you want it to be acidified, you will add dilute sulfuric acid as well to it, okay? So sometimes you will see that it is being written as H+, so that just means acidified. If you want to write down sulfuric acid, that's not a problem as well, okay? So there are this is the two common oxidizing agents used to oxidize our alcohol, but what type of alcohol can be oxidized, okay? For a secondary alcohol, it can be oxidized into aldehyde first, and then later on oxidized to carboxylic acid, okay? For a secondary alcohol, it will be oxidized into ketone, whereas tertiary alcohol cannot be oxidized, okay? No matter which oxidizing agent you use, the tertiary alcohol cannot be oxidized. So I'm going to draw one example for your primary alcohol. For your secondary alcohol, I will give you an example later on. For alcohol, I'm just going to take the easiest primary example first, which is your ethanol. Okay, so if you want to collect your aldehyde, you need to use a specific setup, okay, which is what I'm going to talk about after this. And if you want to collect carboxylic acid, you don't have to worry. You can just heat it under reflux, okay? So when you treat your ethanol with an oxidizing agent, what happens is that it will be converted into an aldehyde, okay? Oxidation is gain of oxygen or loss of hydrogens. In this case, we are losing the hydrogen, okay? More specifically, we are losing the hydrogen here and here. Now, you should not touch anything else that is not the functional group, okay? So your functional group is this hydroxy group, which sits on this carbon. So only the atoms that are on this carbon will be affected, okay? So an aldehyde is when you have a functional group with C double bond O with hydrogen, okay? So you can see that the green hydrogens that I have highlighted are gone. We lose hydrogen during oxidation. So this is primary alcohol, and we call this ethanol. Okay. And we call this a partial oxidation, okay? When ethanol is partially oxidized, it becomes ethanol. And then fully oxidized, it becomes ethanoic acid, right? So this step, again, oxidation, gain of oxygen, all right? So you are adding, let's see. So CH3, that is not your functional group, so you should not change it. C double bond O, and then you add an OH. You are adding oxygen here. Where is the oxygen coming from? It's from your oxidizing agent, okay? So again, I just want to highlight, this is ethanol with the functional group CHO, and then your final product of full oxidation is carboxylic acid, and it is ethanoic acid. Notice that at every step of this oxidation process, I have not lost any carbon, Okay, the number of carbon should stay the same. The structure should stay the same. The only thing that I'm changing is the functional group of alcohol into an aldehyde, aldehyde into a carboxylic acid. Okay, right. So that's what I was talking about, partial oxidation and also complete oxidation, full oxidation, right? So if you want to do the partial oxidation of your primary alcohol, you should set up your reaction to have a distillation part. Okay, so the reason for distillation is that you distill off, you collect any aldehydes that are formed. Aldehydes will be produced first, followed by carboxylic acid, because aldehyde will have a lower boiling point than carboxylic acid. So once you have aldehyde, it will, oh, hey, what happened? Sorry. Once you have aldehyde, okay, so it will, in the gas form, it will try to escape. However, this setup is airtight. Therefore, it just passed through the side arm. And then once it reaches the aldehyde, this part is cold. So what happens? It is being condensed into liquid. It turns from gas to liquid. So once it becomes liquid, then it just falls into the collector. Okay, so that's why we need to use distillation if we want to collect aldehyde. Once we form aldehyde, we collect it straight away. We remove it out of the reaction, because if you don't, then the aldehyde will react further, will be oxidized further into a carboxylic acid. Okay, if you want to collect carboxylic acid from a primary alcohol, you don't need a special setup for it. You just need to have a reflux setup. Okay, so this is your reflux setup. Reflux setup is open. Okay, this is an open air concept. The side arm is not your Liebig condenser. It's not your condenser. That's just to add your reagents inside your reaction mixture. Okay, so that is not part of the collection or whatsoever. So when you have carboxylic acid being produced, the vapor will move up. Okay, and then once it reaches the Liebig condenser, it will then, once if you have any aldehyde, okay, if you have any aldehyde in this reaction, your aldehyde will try to escape. Okay, so aldehyde forming, aldehyde wants to escape. Now, even though that this end of the Liebig condenser is open, once the aldehyde vapor reaches the cold condenser, cold Liebig condenser, it turns into liquid. And once it becomes a liquid, it falls back into the flask. Okay, so there is no way the aldehyde can escape. And once your aldehyde goes back to the flask to react, it will be further oxidized into carboxylic acid. So you don't have to worry. Even if you leave this reaction for too long, the final product will be carboxylic acid anyway. And it's even better so that you ensure that all of your alcohols have been oxidized into the final product of oxidation, which is carboxylic acid. Okay. Okay. Next, the observation. So on your table, there are two reagents, okay, written down, and you need to write down the observation for each of this oxidizing agent, okay, because this oxidizing agent have different starting color and different end color. For potassium dichromate, acidified potassium dichromate, you would first see orange color turning into green. If you see this color change orange to green, that means alcohol has been oxidized, okay? So oxidizing agent oxidizes alcohol. I don't know if you have learned about oxidizing agent, but when an oxidizing agent oxidizes another species, the oxidizing agent itself gets reduced. Okay, so it oxidizes another person while itself is getting reduced. So here's what happens to potassium dichromate. It gets reduced from Cr2O7 to minus into chromium 3 plus. So this is called the dichromate ion. So that is the species that is responsible for the orange color, not the chromium. Okay, it is the chromium in the dichromate ions. And the green color is due to the presence of chromium 3 plus. So this observation is actually useful or good to be used as a test. Okay, that's potassium dichromate. What if we use acidified potassium manganate? I think you all know the color of potassium manganate initial color, which is purple to colorless. The purple color is caused by the manganate ion, MnO4 minus, and colorless is because of Mn2 plus. It doesn't mean that there's no longer any manganese in the reaction mixture, okay? Now, when you see the purple turns into colorless for potassium manganate, that means oxidation has occurred for the alcohol and reduction has occurred for the manganese. So in this process for the dichromate and the manganate ion, what happens is that they are being reduced, okay? Right, so if you want to copy this down, you can pause your video now. Right, next, I am going to show you the example of the oxidation of ethanol. Okay, so I've already written down for you the whole oxidation from partial all the way to the full oxidation. But now we're just going to look at the equation for the partial oxidation. Oxidation is the process of either gaining oxygen or losing hydrogen. In this case, we are losing hydrogen to hydrogen, okay? And the oxygen is from the oxidizing agent to form your side product, H2O. If you're wondering where we got the oxygen from, it comes from the oxidizing agent here. Okay, and your alcohol has turned into an aldehyde. So you go from ethanol to ethanol. For full oxidation, if we use ethanol as our starting material as well, to go all the way in the presence of heat, of course, right? You will get an ethanoic acid plus water. Okay, so what happens here? You are gaining hydrogen, you are gaining oxygen and you are losing hydrogen. Okay, so if I just highlight the functional group and notice that the other parts of the molecule does not get affected, okay? It stays unchanged. So the most important thing is that if you want to collect an aldehyde at the end of your reaction, you need to use distillation as your setup. The condition is important here. Whereas if you're expecting to collect a carboxylic acid, then you just need to heat it under reflux. Okay, so if you don't specify the condition, then you are most likely to get carboxylic acid. It is important that if you want to collect an aldehyde, please specify the setup to be a distillation setup. If you don't specify, you may be penalized, you may lose marks, or it is assumed that you are expected to collect carboxylic acid, right? You can pause your video here. Moving on to the next type of oxidation, secondary alcohol can be oxidized into a ketone, if you still remember from the first slide that I showed you earlier on. The reagent is the same. You can use potassium manganate or you can use acidified potassium dichromate. There is no specific setup. You will just heat it under reflux. So what happens is that, again, we are only interested in the hydroxy group and where the carbon where the hydroxy group is attached to. Okay, so you are oxidizing a secondary alcohol into a ketone. If you still remember the ketone, the functional group of ketone is CO attached to both carbon. Okay, so that means in this case, you have lost hydrogen. You notice that you lost the hydrogen and now your oxygen becomes a double bond. So this is the ketone functional group. And of course, the side product is water. You get the hydrogen, 2 hydrogen from the alcohol and the oxygen from the oxidizing agent. Actually, if you study about the mechanism, the oxygen would have come from the alcohol, but you don't have to worry about the mechanism for now, okay? And it stops at ketone. Ketone cannot be further oxidized, unlike your primary alcohol. So that's the final product of oxidation of secondary alcohol. So you don't have partial oxidation or full oxidation, okay? Observation would be the same because you used the same oxidizing agent for the primary alcohol as well. If you're using potassium dichromate, you would expect to see orange turning into green. If you're using potassium manganate, then expect your purple solution of potassium manganate to be decolorized. Okay, please do not use the word transparent. So here's an example again of your oxidation of secondary alcohol. Now, in your notes, this example of secondary alcohol is at the bottom of the page, which comes under tertiary alcohol. Okay, so can you please move that diagram? I think it's this diagram or a different one. Do I have it here? I don't have it. Okay, so that example at the bottom of your page, can you please move it up to or you just cancel it, all right? Because that is an example for oxidation of secondary alcohol. The next one is tertiary alcohol. Tertiary alcohols cannot be oxidized at all by potassium dichromate, by potassium manganate, or any other oxidizing agent. Okay, the reason for that is because there is no hydrogen atom bonded to the carbon with the OH group. So if you look at this tertiary alcohol, okay, usually we lose hydrogen here, here, or here, right? If you look at the primary and the secondary. Now you do not have a hydrogen. The carbon is directly bonded to another carbon. So it will be too far if you lose that hydrogen because that hydrogen is now on a different carbon. So you usually lose the hydrogen from the same carbon where your functional group is sitting. So because of this, since there is no hydrogen attached to the same carbon, then it cannot be oxidized. You cannot lose hydrogen. After all, that's the definition of oxidation, right? You lose hydrogen, you gain oxygen. Okay. This has an important implication actually in testing of the types of alcohol. Okay, so far we saw that primary and secondary alcohol can be oxidized, and we were able to observe the color change, whereas the tertiary alcohol cannot be oxidized. So whenever we have a reaction in organic chemistry that produce an observation that can be seen by the naked eye, we use this as a test. Okay, so it's just a primary test. It's not a confirmatory test. Okay, so how can we use this as a test? So if primary alcohols and secondary alcohols can be oxidized, you would have seen color change. Whether you use a dichromate or you use your acidified manganate, okay, you would see orange to green, or you would see purple to colorless. Whereas if you were to add oxidizing agent to a tertiary alcohol, there wouldn't be any reaction. So you would expect your potassium dichromate to stay orange or your potassium manganate to stay purple. So from here, you are already able to eliminate the tertiary alcohol. If you are given 3 unknowns alcohol and then asked to identify which one is tertiary alcohol, of course, it would have to be the one that doesn't change color when added oxidizing agents. Okay, so for example, here we have a propan 1-ol, propan 2-ol, and 2-methyl propan 2-ol. So I'm guessing we are using potassium dichromate here. Okay, so the oxidizing agent that we use, potassium dichromate. So you can see that at the end of the reaction, your orange solution of dichromate has turned green. So that means, yes, oxidation has occurred. In propan 2-ol, likewise, oxidation has occurred as well. However, in the third test tube, oxidation has not occurred. There is no change in color. So that means this must be a tertiary alcohol. Okay, how do you differentiate primary and secondary? Well, that's you have to use a different test for that. Okay, so this oxidation test when adding oxidizing agent is actually a good primary test to eliminate your tertiary alcohol. Okay, now in the next page, on page 9 of your notes, there are 5 questions for you to practice on the structural formula as well as the oxidation reaction of your alcohol. So I want you to leave your answer in structural formula. You notice that there's a big space at the bottom of your page. Use that big space, utilize the space to draw your displayed formula. If you can work it out, that's fine. Okay, but I want you to make it a habit, since this is your notes, draw the displayed formula and work out the oxidation products, if there is any. So to answer this question, 5 questions, if there is oxidation, continue with the process. If there is no oxidation, you just cross out. For example, say after this molecule, it cannot be oxidized, I will just cross it. Okay, so how do you do this question? I would want you to start with drawing the structure of the given molecule. Okay, I know it's in structural formula, but let's face it, we know that it's not easy to visualize things in a structural formula. Okay, so I've got my CH3 and then I've got my CH, so that's my CH, and CH3 is in a bracket, so that means my CH3 is a side chain. To continue, I have CHO. Now, whenever you see CHO, that is a hint that it is an aldehyde. Okay, so I will just write aldehyde here, highlighting the functional group. Okay, so that means I have to find the alcohol that produces this aldehyde upon oxidation. So I just have to do things in reverse. Okay, keeping the rest of the molecule the same, right? Because that's not the functional group, so I should not change anything from there. right? And this aldehyde would have come from an alcohol. So I will just, my carbon will still have to be there. And then OH, H, H. So I am just adding hydrogen. If you want to know my original bond, it's there. Okay, and I'm just adding hydrogen because during oxidation we gain hydrogen, right? So this is my primary alcohol. Just check that it is a primary alcohol and check that you have not changed the structure except for where the functional group is. Same thing, because it is an aldehyde, it comes from a primary alcohol. It can be oxidized further into a carboxylic acid. The trick is to draw the part of the molecule that doesn't get changed during oxidation. Okay, so I've got that part. And from aldehyde, I want to form a carboxylic acid. So I just write down COOH and making sure that I have not changed other parts of the molecule. Okay, it's just the functional group that I have changed. And then from here, I want you to practice writing down your structure formula. So I would write down CH3, and then I've got a CH. I've also got a CH3 as my side chain, CH2OH. Okay, try to write down your structural formula so that your functional group can be seen instead of writing down COH3. Okay, I mean, there's nothing wrong with it, but I want to show that it is an alcohol. So I write it as CH2OH. Next, writing down my carboxylic acid from my structural formula. Writing down the structural formula of my carboxylic acid from my displayed formula. CH3, CH, and don't forget the other CH3, COOH. So you can clearly see the functional group alcohol, aldehyde, carboxylic acid, and that is your oxidation of primary alcohol. Okay, so you don't have to worry about the naming here, carboxylic acid. Right? So that's the first example. Okay, for question 2, 3, 4, and 5, I'll leave it to you, but make sure that you draw the structure like this, and then you write down the structural formula correctly. If you cannot do your structural formula, I suggest you to number your carbon. So carbon 1, carbon 2, carbon 3. Okay, and the CH3 group is sitting on carbon number 2, which is this one. Yeah. Okay, so if you want to copy this, you can pause here. Okay, the last reaction, and it's the last page of this topic as well. It is a short topic, but there's a lot of things that they can ask you from this topic, okay? And it's usually connected to the previous topics and the topics that we are going to cover next, okay? So organic chemistry usually involves or connect a few topics together because there's a connection, right? The different functional groups can be present in one molecule and can be asked in the same question, okay? Right, deduce the presence of a CH3CHOH group in an alcohol. So this is a specific part of the alcohol that can react in this reaction. Okay, so this CH3CHOH can react with alkaline iodine to form a yellow precipitate of triiodomethane and an ion RCO2 minus. Okay, so I'll talk about this RCO2 minus ion when we look at the reaction later on. But first, this reaction is called the iodoform reaction, or there's another name for it, which is the triiodomethane reaction. The reason for that name is because of the product that gives you the yellow precipitate. The species that gives you the yellow precipitate is a triiodomethane. Triiodomethane is CHI3. Okay, so it comes from a methane group, but 3 of the hydrogens in methane has been replaced with iodine. Okay, so that's why it's CHI3. Okay, so only alcohol with the CH3CHOH group will give yellow crystals or yellow precipitate of triiodomethane. So it's not just any alcohol. So what's the requirement? If we look at this box where it says the carbon must have an OH, it must have a CH3, and it must have a hydrogen. So that is the most important requirement: a COH, a CH3, and a hydrogen attached to that same carbon. The fourth bond doesn't matter, can be hydrogen, can be carbon, can be some other things, okay? But usually it's an alkyl group, okay? So that's why we write it as an R, where it is an alkyl group, or it can be a hydrogen as well, no problem. Alkyl group or hydrogen atom, okay? But the most important thing is this 3 bonds, because only when you have a molecule and the carbon is attached to a hydroxy group, a methyl group, and a hydrogen group, then only positive result or positive test of the iodoform reaction will be shown. Okay, so what's the reagent that you need? You need if you read just now, alkaline iodine, that means your iodine has to be combined with an alkaline solution, which is your sodium hydroxide. Okay, so when you add aqueous sodium hydroxide, you mix it with iodine and then you just warm it. So then the iodoform reaction will happen to your to this type of alcohol. Okay. Right. So if you look at the structure, your methyl group has to be next to the carbon attached to the hydroxy group. Okay, so methyl group next to carbon attached to OH. Okay, what if you have all CH3? Can this react in iodoform reaction? Cannot. Why? Because you are missing the hydrogen. You must have all 3 present. Okay, if this was a hydrogen, this is a hydrogen, and this is also a hydrogen, this molecule cannot react in an iodoform reaction. Why? Because the methyl group is missing. Okay, so you must have all 3 in one molecule. So that means if R is an alkyl group or a hydrogen atom, that means this alcohol can only be a primary or secondary alcohol. Okay, why can't it be a tertiary alcohol? Well, if you have CH3 and another CH3, then this reaction will not happen because you do not have a hydrogen. That hydrogen is vital actually, because what's going to happen in this reaction is that your alcohol will be oxidized. So that is fitting to say that it only works for primary or secondary, but not tertiary or secondary alcohol only. not tertiary. Okay, so if I just separate this. So tertiary alcohol cannot undergo iodoform reaction. Okay, so I'll show you what happens in the next slide. The condition is to warm it. You don't even have to heat it very, very high. Okay, so this is what happens. This reaction is used as a test for the presence of CH3CHOH group. So whenever you see a positive result with alkali iodine, that means there is a methyl group next to your hydroxy carbon with the hydroxy group. Okay, so what's happening here? First, so let's check if butanol can undergo iodoform reaction. So that's my highlighted carbon. It has OH group. It has a methyl group, CH3, and it also has a hydrogen. So then, yes, this molecule can undergo iodoform reaction. What about the rest of this molecule, the fourth bond? Well, I don't have to worry about that. Okay, as I said, the first step is to oxidize the alcohol. So oxidation first the alcohol, so I will not specify primary or secondary, but in this case it's the secondary alcohol. First, the alcohol will be oxidized to a ketone. Okay, so a ketone or an aldehyde, it doesn't matter. Okay, so what happens during oxidation? You lose this hydrogen, and then because it's a secondary, you form a ketone. That means you must have double bond on the oxygen, and you lose this hydrogen as well. Okay, so I'm just going to highlight that using a different color, COOH. Okay, and now that bond becomes C double bond O. Okay, and you can see that this is a methyl ketone. In the next topic, we will learn about this methyl ketone. It is the functional group, or it is the part of the group that actually reacts in an iodoform reaction. Okay, so the first step is what we call the halogeno alkane. So your oxidized product of the secondary alcohol, which is your butanone, will then react with the alkali iodine. So this is where iodoform reaction is happening. Okay, this first part is strictly speaking not the iodoform reaction yet. Okay, so that's just to convert your alcohol into a ketone, right? But the step 1 and step 2 is where your actual iodoform reaction happening. Okay, so on the first step, this is where your iodine and your sodium hydroxide is working. What happens is that we are halogenating the methyl group. Okay, so we are halogenating the methyl group, the CH3 group. We replace all the hydrogen with iodine. Okay, so all 3 hydrogen atoms in the methyl group next to C double bond O will be replaced by iodine atoms. So you can see if I label iodine as green, so you get a CI3 here. Okay, the first step is the halogenoalkane. The second step, we take this species, this molecule, and it is reacted with sodium hydroxide, aqueous sodium hydroxide further. This process is called the hydrolysis. So hydrolysis means we are breaking some bonds in the presence of water. Okay, so the water comes from the aqueous the AQ part, the aqueous part of the sodium hydroxide. Okay, so what happens is that then your Ci3 will pick up a hydrogen and then to form CHI3. So if I highlight this whole thing pink, okay, then in the product, please take note that there is an additional H atom from your Ci3. Okay, so it's not just strictly Ci3. And then the salt that you form is the salt of the rest of the molecule. Okay, so this is actually a carboxylate salt. You count the number of carbon. Okay, so if I just number my carbon 1, carbon 2, carbon 3, and here you have carbon 1, carbon 2, carbon 3. I would draw the structure for this. CH3, CH2, C double bond O, O minus. Okay, that sodium came from the sodium hydroxide here. Okay, so this salt is now called 1, 2, 3. It's got 3 carbon. We call it a propanoate. Okay, so 3 carbon, carbon 1, 2, and 3. We call it a propanoate salt. And then the other product is the CHI3. And this is what we call the triiodo, since there are 3 iodine. Methane, because there's 1 carbon. And this is the species that is causing or producing the yellow precipitate. So when you add alkali aqueous iodine to an unknown molecule and you see yellow precipitate, that means that unknown molecule must have this structure. Okay, that's the only possible conclusion or implication that we can get from this reaction. Okay, so this is why, because we are producing yellow precipitate, it is used as a test. As I mentioned earlier on and many times, that whenever we can see an observation in an organic reaction, we use that as a test. Okay, so a yellow precipitate with aqueous iodine with sodium hydroxide would indicate that the starting material contains the CH3 CHOH functional group. Sorry, it's not a functional group, but it's a part, the structure in a molecule. Okay, the functional group is the alcohol, right? But it is not all alcohol will give a positive result with iodoform reaction. Only this type of alcohol, your primary and secondary, specifically the one that has a methyl group next to your carbon that is attached to hydroxy group. Okay, so I'll leave you to copy this down. Don't forget to copy the observation, what that yellow precipitate indicates, as well as this reaction. Okay, don't forget the first part is the oxidation bit, and then only you start step 1, which is halogenation of the methyl group next to the carbonyl carbon, C double bond O. All the 3 hydrogens in that CH3 will be substituted with iodine atoms, Ci3. Okay, not I2, even though iodine is I2, but 3 iodine atoms will be substituted into that molecule. Okay, and then the next part, step 2, is the hydrolysis, where you break the bond to release a triiodomethane, which is your CHI3. Okay, right. So for your task today, of course, after this, you will fill in the test questions. As usual, you can find the link in the description box. And another assignment for you is to complete this exercise on page 9. Okay, so you have question 2, 3, 4, and 5 to complete. Draw first and then write down the correct structural formula for question 2, 3, 4, and 5. Okay, so I'll leave it here. You can pause this slide, and I forgot there's the one last slide. So if you want to copy this down, you can pause here. This is the last slide. It's the things that I've already said to you, but I don't want to just leave it like that. Tertiary alcohol will not have a positive result with iodoform because the hydroxy group attached to the carbon is only attached to all 3 carbon atoms, and there is no hydrogen atom. Okay, it doesn't have this structure. Your tertiary alcohol will never ever have this CH3 CHOH structure. Okay, so that is all for today. Assalamu alaikum, and thank you, everyone. Oof. Are you hot?